the students are here, so we are going to get started. So good morning, everyone. Trying to admit most people here, okay. And so today we have Professor Linyue Gao, who is going to talk about wind energy in cold climates, which is ad hoc for the day that we have today here in Denver. So Professor Linyue Gao just joined us this semester here at CU Denver as an assistant professor in mechanical engineering. She graduated from Iowa State University in 2019, and then she's been in a couple of institutions at the University of Minnesota, as well as California State University in Sacramento. And as I said, she joined us as an assistant professor at this semester here at CU Denver. And without further ado, Dr. Gao, the stage is yours, so please go ahead. You might share your screen so we can see your slides, and then you can get started.
Thank you for your introduction.
Uh-huh.
Could you please enable screen sharing?
Yeah, I have to do that. Sorry about that. Yes. All right, so now you should be able, Dr. Gao.
Yeah, it works. Can you see the shared screen?
We can, yes.
Yeah, great. Yeah, so it is my pleasure to give a talk on my research. And actually, my research interests are experimental flow dynamics, especially on the flow diagnosis and the instrumentation. And today I will introduce my research focused on the application on renewable energy, especially for the wind energy. So today I'm going to talk about wind energy in cold climates. So as you can see from this map, the purple color highlights the cold climate regions. There are lots of wind farms built in this region to take advantages of the abundant wind resources and low population density. The wind turbines built in these cold climate regions may suffer severe icing issues in winter, and about 30% of the total world's installation are affected by the icing issues, and particularly for the wind farms located in mountainous sites and coastal sites. Wind turbine icing presents the most significant threats to the integrity of the wind turbines, and as you can see from those photos, the ice accretion on wind turbine blades can alter the aerodynamic profile of wind turbine blades and degrade the aerodynamic performance of wind turbines, such as the drag increase and lift decrease. And under severe icing conditions, wind turbines usually have to be shut down to avoid mechanical damages. And the downtimes due to icing may last for days or even weeks, which can lead to significant economic losses for wind farm operators. And in addition to the power output penalties, the uneven ice accretion along the wind turbine span can also cause the edgewise vibrations or even imbalance, which may significantly shorten the lifespan of wind turbines. And in addition to those direct effects, icing may also cause some secondary effects, such as the safety issues due to the falling or projected ice chunks. From a physics point of view, there are mainly two types of ice. We can call them Rime Ice and Glaze Ice. And the ice type mainly depends on four parameters: the ambient air temperature, incoming flow velocity, liquid water content, and droplet size. As you can see from the animation on the left, when the supercooled water droplets impinged onto the blade surface, if they could freeze immediately, we call it Rime Ice formation. Rime Ice usually has an opaque and white appearance and can follow the streamline shape of an airfoil. On the right side, here is an animation of glaze ice formation, with large number of supercooled water droplets impinging onto the airfoil surface. Tremendous latent heat of fusion will be released, associated with the rapid solidification of the impacted water. Since the heat transfer process over the airflow surface could not be able to remove all the released latent heat of fusion immediately, only a portion of the impinged water droplets could freeze into ice upon impact. The rest of the impinged water mass could stay in liquid state, as driven by the boundary layer airflow over the airflow surface. The unfrozen surface water will run back along the airflow surface and to form those rivulet flows. And the rivulet flows of the run-back surface water would be frozen into ice eventually at the further downstream locations. Due to the wet nature, the glaze ice usually has the complicated shapes and difficult to be accurately predict, and it's difficult to be removed once built up on the airflow surface. And in my research, I mainly focused on the glaze ice formation. Here it is the outline for today's talk. First, I will talk about how to quantify the aerodynamic icing process, especially for the glaze ice formation. Second, I will show you how to experimentally characterize the ice-induced aerodynamic penalties during the dynamic icing process. After that, I will show you a fields campaign for the utility scale wind turbine icing. The last part is about the anti-icing or de-icing strategies. So first, quantification of the dynamic ice accretion process over wind turbine blades. So as you can see from this figure, here it is a wind turbine blade, and you can see the ice formation on the wind turbine blades. And this is under a glaze icing condition, so you can see the water run back in those regions. And under the glaze icing condition, you can consider we have the mixture of ice and water. So we have two questions to answer. The first one, how to get the three-dimensional shapes of the ice and water structures experimentally. The second question, how to separate water from ice. So here, we first introduced the DIP technique for characterizing the icing process. DIP is short for digital image projection, and this technique is non-intrusive structure light technique that can be used to reconstruct the three-dimensional features of the object. This one is the sketch of the principle for the DIP technique. We use a digital image projector to project the grid patterns onto the reference plane, and we use a high-speed camera to record the projected image patterns. If there's an object on the reference plane, the grid patterns will be deformed. The deformation has a linear relationship with the thickness of the object. So based on it, we conducted a series of experiments at the icing research terminal at Iowa State University. And here listed the technical parameters for the icing research terminal. In comparison to the traditional wind tunnel, we have two additional systems for the icing wind tunnel. The first one is the spring system, so we can use it to generate the droplets. And the droplet size ranges from 10 to 100 micrometers, and we can control the liquid water content from 0.05 to 10 gram per cubic meters. And also we have a cooling system, so we can control the temperature down to -25 degrees C. So using this wind tunnel, we can duplicate a wide range of the conditions from Rime Ice to Glaze Ice. And for the DIP technique, we need to do the detailed calibration process. And here it is the calibration results we get. So we derive the linear relationship between the object's thickness and the image distortion. And here shows some preliminary experimental data. This one, it is the raw image of the airfoil surface. And this one, it is the raw image for the airflow surface with ice structures accreted on it. So you can see the deformed patterns in this image. And this one shows the preliminary results for the DIP measurement. And in this one, the color here indicates the thickness of the object of the ice and water. So this slide shows the dynamic icing process over the blade surface. The left side is the raw images, while the right side is the processed data. As you can see, we successfully characterized the droplet impingement, ice formation, and the water transport process. And here shows more experimental data under different conditions. And we change the incoming flow velocity. And as the incoming flow velocity increases, the wind-driven rivulet flows can reach further downstream locations. To provide more quantitative information for the 2D modeling development and validation, we further integrated the measurement data along the span-wise location. And by comparing the data at different time steps, we can directly see the motion of the wind-driven flows. And also we can see the thickness increment during the ice accretion process. Here comes to the second question, how to separate water from ice based on the experimental data. As you can see from this sketch here, we assume the ice layer is stable, while the water layer is moving, driven by the boundary layer flows. Therefore, by comparing the sequence images, we can identify the moving parts and use it to represent the amount of water, and the unmoving parts will be the ice. And based on it, we can find the ice accretion as a function of time. And we found actually it has a linear relationship with respect to time. If you are interested in our DIP technique and interested in icing physics, you can directly go to our paper published on International Journal of Heat Mass Transfer. So after we get the quantitative information of ice, we would like to know the blade's aerodynamic penalties introduced by ice. So previously, what people did, people usually molded the ice airflow shapes and casted them for the aerodynamic property study. However, there are multiple limitations for those types of technique. We know the ice structures that are so fragile and could be damaged during the molding process. And for each model, they can only represent one moment's results. So those type of method is so expensive. So here we come to two questions. The first one, how to characterize the ice-induced aerodynamic performance degradation during the icing process. We not only want to know one moment's results, we want to know a series of results. And also we want to know the effect of anchor attack on the ice-induced aerodynamic penalties. So here, to get the aerodynamic performance, we want to know the lift, we want to know the drag. And what we can do, we can use the force transducers to help us to do the measurements. And we know the force transducers can measure the force components vertically and horizontally. And we know the lift force, it is vertically and it is perpendicular to the incoming flow direction, and the drag force, it is along in parallel to the incoming flow direction. However, for the lift force, as you can see from this sketch, it is coupled with the weight of the test model. And during the icing process, the lift force is coupled with the weight of the test model, and it is coupled with the weight of ice. However, the weight of ice is changing. So how can we uncouple the lift force with the weight of ice and weight of model? So what we can do, we can use the tear test under the unloaded conditions so that we will know the weight of ice at a specific moment, and we can know the weight of model. And also we conduct a pilot experiment to measure the weight of ice in every 100 seconds and supplement the data using a linear interpolation. This linear interpolation is based on our finding in the previous study because we found the weight of ice has a linear relationship with time. So in addition to the lift force, the drag force, we also want to know the flow structures. So what we did, we use a PIV system to conduct the PIV measurements. PIV is Particle Image Velocimetry technique, and we can use it to measure the velocity with respect to time. We use the ND-Young's laser to illuminate the flow and use the high-speed camera to take images. Notice that during the ice accretion, we directly use the water droplets as the seeding particles for the PIV measurements. Here shows the results for the PIV measurements. So as you can see, this one is the airfoil, and we have the flow around this airfoil. Before starting the ice accretion process, the incoming flow was found to conform well to the streamline profile of the wind turbine blade model when the test model was mounted as an off-tech of 10 degrees. And shortly after the ice accretion process starts, well, the evidence as structures were found to create over the both upper and lower surfaces of the test model. The irregular shaped S structures created over the suction sides airfoil surface could affect the development of the boundary layer flows over the test model significantly, which results in the air flow separation over the airfoil surface near the airfoil trailing edge, as you can see here. As time goes by, with small supercooled water droplet impinged onto the airfoil surface, the irregular shaped S structures created over the test model were found to grow up rapidly. As a result, the flow separation zone formed over the airfoil surface were found to expand further upstream and become bigger and bigger. So the formation and the expansion of the formation and the expansion of the large-scale flow separation zone over the airfoil surface as induced by the accretion could cause the dramatic degradation on the aerodynamic performance of the wind turbine blade model. So here shows the performance degradation induced by the accretion. This one shows the lift coefficient as a function of time, and this one shows the drag coefficient as a function of time. We can see, as expected, as the time goes by, lift decreases and drag increases. And we can see the performance degradation was found to be a strong function as of the angle of attack of the blade model, with more significant degradations at lower angle of attack. So inspired by these findings, actually we proposed an active pitch control strategy for the wind turbine icing mitigation by leveraging the significant difference in icing-induced performance degradation at different angle of attacks. So if you are interested in PIV measurement, if you are interested in the aerodynamics related to wind turbines, please feel free to go to our paper published on renewable energy. And also, based on this funding, for the pitch control strategy, we was filed needs for a patent. So you should be able to find it online.
Jean, can I ask you a question?
Mm-hmm.
Oh, sorry, Lynn, sorry, not Jean, sorry. So you're mentioning the, to avoid this degradation, you might use pitch control, but that pitch control is also used for maximum power point tracking and things like that. So the idea is to use the same actuation, but just with a different control objective. Is that more or less what you're referring to?
Yeah. So for the wind turbine pitch control, we can set the bias, a small bias value to the current pitch control algorithm under different conditions, and we can adjust the value of the bias to get the optimal power output under different icing conditions.
I see. Yeah, perfect. Yeah.
So lots of lab scale experiments, and we know the lab scale experiments, they are under the well-controlled conditions. It's not that representative to the real conditions. So based on that, we conducted a field campaign in a mountainous wind farm. So here shows the layout image animation for this wind farm. So for this wind farm, the installation capacity is 50 megawatts, and it is a mountainous wind farm, and the wind turbine capacity is 1.5 megawatts. And for this wind farm, the icing probability was found to be about 85% in winter. And this one shows the wind farm layouts, and you can see those marks. Those shows the locations of those wind turbines. And here shows more pictures related to wind farm. And you can see the wind turbines were enveloped by the thick freezing fog in winter. And also for this one, for each mark here shows the each wind turbine. Okay, and during the test, we use a UAV system to characterize the snapshots of the ice wind turbine blades. And also we have access to the wind turbine SCADA data. So that means we know all the operating parameters related to the wind turbine. So here we conducted a campaign in this wind farm for a 30-hour icing event. Here it is a video. Let me click on it. Okay, so can you see this video? Okay, so we use this UAV system to characterize the ice accretion on wind turbine blades. So based on the obtained images, can you see it?
Yeah, we can.
Yes.
Mm-hmm. So for the UAV system, we can adjust the elevation of it. So we can take a series of images along the wind turbine blades to get the high resolution results. And based on the obtained images, we can extract the ice layer thickness along the wind turbine blade's leading edge. Okay, let me stop it. Okay, and so based on the images, we extracted the ice thickness along the wind turbine blade thickness. And we found that the ice was accumulated over the entire wind turbine blade span. However, the tip region with more ice structures and the ice layer thickness near the tip region can reach up to 0.3 meters under this 30-hour icing event. And in addition to that, we know we have the wind turbine SCADA data, and based on it, we found that wind turbine were discovered to rotate substantially slower and even shut down time to time during the ice event, which results in up to 80% energy losses during the entire ice event. And if you are interested in our UVV measurements, please go to our paper published on the renewable energy, and also our work was reported on PNAS. Okay, so lots of things about the icing physics, ice accretion. So we wonder whether we can mitigate the icing events. So we want to do the development, we want to develop the anti-icing strategies. And currently in wind energy industry, the wind turbines, some of the wind turbines are equipped with ice protection system, but all of those systems are thermal-based system. They are using the hot air injection or resistive heating. So that means they will increase the surface temperature of the wind turbine blade to melt the ice structures created on them. Okay, so however, those strategy, it is really energy consuming. Is there any other methods that we can use? So today I want to introduce you the passive techniques, especially based on coating method. So for traditional wind turbines, for the surface, they are coated with the hydrophilic surface. So this one, it is the standard one. And today I want to show you two different kinds of coatings. One is the superhydrophobic coating, which is inspired by the lotus leaf. And for the superhydrophobic coating, we have the nano and macro scale roughness structures on them. And another one is the slip surface inspired by the peat plant. And as you can see from this table, in comparison to the traditional surface, the superhydrophobic surface and the slip surface, actually they have much lower ice-adhesion strength. That means they are much more, we can remove the ice structures much more easier from those kind of surface. In addition to that, it will significantly affect the droplet impact process. As you can see from this animation here, if we have the water droplet impinged onto the hydrophilic surface, the impacted water will spread out rapidly to form the pancake-like structure. And if we have those kind of structure, that means it is very easy to freeze onto the surface. And let's see the other two. After the water droplet impinged onto the superhydrophobic surface or the slip surface, we can see it will be spread out rapidly to form a very thin water film over the impacted surface. However, instead of forming the pancake thin water film over the impacted surface, the outspreading water film will found to be break into many tiny droplets and bouncing off from the impacted surface immediately and splashing into the ambient air over the impacted surface. So here we conducted a series of experiments in the icing wind tunnel, and this one is for the traditional surface, the hydrophilic surface, and we can see the ice structures are created on it. However, for the other two surfaces, the superhydrophobic surface and the slip surface, we can see only ice accretion around the leading edge. There's no ice formation in the downstream locations. Actually, we have this one is related to three different kinds of reasons. The first one is related to the bouncing mechanism for the superhydrophobic and slip surface. And another one, it is related to the smaller capillary force for the superhydrophobic and slip surface. And for the superhydrophobic surface, it is about 20% of the traditional one. And the third reason is related to the reduction of the ice adhesion. And for the slip surface, it has a much lower ice adhesion, also for the superhydrophobic surface. So we can see the superhydrophobic surface or the slip surface, they can reduce the ice structures created on the blade surface. However, they have very limited anti-icing performance near the leading edge region, because we know near the leading edge region, actually the aerodynamic forces are very limited. Near the leading edge region, they are close to the stagnation points. There, the wind speed almost zero, so the aerodynamic forces are too small to overcome the axial tension. So based on it, is there any way that we can optimize the performance of superhydrophobic surface or slip surface? So here we consider a combination of the traditional electrical heating methods and the superhydrophobic surface. Okay, so based on it, we propose this hybrid methods. So we coated the entire blade surface with the superhydrophobic coating, and to avoid the ice accretion near the leading edge surface, we will install the heating film near the leading edge region. And here shows the results. You can see if we only have the leading edge heating film, we will have the downstream ice accretion. However, based on our hybrid methods, we will keep the surface free of ice. And we conduct a series methods and using the infrared camera, so we will know the temperature at different locations. And we found that actually near this region, we also have very high temperature. That means actually we can minimize the size of the leading edge heating film. And based on a series of experiments, we found that actually we can use 10% the heating film covering the 10% of the leading edge region, so that we can save about 90% energy based on this novel method, which is very promising for the wind turbine icing mitigation. So let's do a quick summary of this talk. So first, I introduced the quantification methods of the dynamic icing process. And I show you how to characterize the aerodynamic performance degradation. And I show you an evaluation of the performance degradation for a utility scale wind turbine. And also, I show you a novel strategy, a heating coating hybrid strategy for the wind turbine icing mitigation. So if you are interested in the wind energy or other sources for the renewable energy under the icing conditions, you can go to this book. So we just published this book last year, and here it is the link for the book. So in this book, it covers the wind turbine icing physics and de-icing strategies, not only the technique I mentioned today. For example, it also covers the wind power forecasting under icing conditions, and also it covers other type of anti-icing strategies, for example, the plasma-based anti or de-icing strategies. Okay, so that's all for my talk. Thank you. And any comments or questions?
So any questions from the students?
So Noah does have a question in the chat. The question is to model the water droplets in some sort of an element and analysis tool used, or is it in a different application?
So today I'm mainly showing you the experimental measurements related to the water droplets or related to other things. And to do the measurements, to do the modeling parts, There are mainly two sources that you can do the modeling related to icing. There's a software called Linyue Ice, and you can directly use it to do the icing modeling. And for that software, you can register it, but you need to be a US citizen to download and use that software. And it is a very powerful tool for icing modeling. And another tool is ANSYS FastNap. And for that, you can also use it for icing modeling. And it is a CFD-based modeling. And for the water droplet modeling, I don't know which parameters you care about. You care about the flow dynamics related to needs or other parts. If you are interested in the flow dynamics related to the water droplets, such as droplet impingement, the droplet spreading upon the impact, you can either use OpenForm. OpenForm is an open source CFD-based modeling tool that you can use. And there are lots of researchers use on it. And for that one, it is based on the finite volume method, not finite element method. Because we know if you care about the solid mechanics, most of it's based on the finite element analysis. But for the fluid dynamics, people prefer to use the finite volume based method.
So I also have another question, Dr. Gao. So when you talk about degradation, I understand that you mean that the amount of power that the wind turbine is generating goes down. But what are we talking about? Like 5%, 10%, just ballpark? Degradation is like how much down is going the power that you're generating? Yeah, I'm just curious about that number. Of course, it depends on the amount of ice. I would understand that, but ballpark, you know.
Yeah, and for example, under an icing event, for the icing event, it may last for days or last for even a couple of months. It depends on the icing condition and depends on the location of the wind farm. And if it's the wind turbine shut down for a couple of days, that means the wind turbine will generate zero energy during the couple of days. So that's why people prefer to equip the ice protection system for those kinds of wind turbines in the cold climate regions. And for the thermal-based ice protection system, for an icing event, during the icing event, that means the wind turbine needs to keep this system on during the entire icing event.
Right.
So it is really energy consuming.
Okay, so so you're saying that when they have ice on, they're shut down? Is that what you're saying?
If that wind turbine are not equipped with ice protection system.
I understand, but if it is equipped, then I understand you have to use some energy to de-ice, but then the net output power is positive.
Mm-hmm. Yeah, I got your points. So I would like to answer it from 3 points. The first one is the current status in United States. I would like to say for almost all the wind farms, there's no wind turbine equipped with ice protection systems so far. So for the ice protection system, it is still a new system. The second part, if there's no ice protection system, for most of there are two kinds of strategies, control strategies for wind turbines. The first one, the wind turbine will immediately shut down to avoid the mechanical damages. And it is a call for the wind farm operator. Another strategy, if the icing is not that severe, the wind farm operator will keep the wind turbine running until it cannot generate any energy. And the third point related to this question is, if we keep turning the ice protection system on, for example, the thermal-based system, usually they can shorten the wind turbine icing event, but usually they need extra energy to power this wind turbine.
I see. Thank you. Thank you. Yeah. So, is there another question on the chat? Because Maxi, because my computer is acting funny. I cannot open the chat.
Yeah, so there is one more question. The question is, how much energy is required for heating the blades versus how much energy the wind turbines produce?
That's kind of like the same question.
Yeah. So
I have some question related to the wind turbine icing. Because the wind turbine blade is basically very similar to aircraft's wing, right? So they are. I was thinking, since you mentioned the pitch angle can be changed by the wind turbine, right? But for aircrafts, sometimes they have some high lift device, for example, like leading edge slats or leading edge slots. They also can change the flow speed over the wing. As far as I know, I haven't seen any wind turbine equipped with that kind of device. But is that possible to equip that kind of device to help to de-ice?
Yeah, that is a very good question. Actually, most ice protection system or anti-icing strategies for wind turbines are borrowed from the aircraft industry. However, there are some difference between the aircraft wind icing and the wind turbine icing, because for wind aircraft, most of the wings of the aircraft are made metal materials. However, for wind turbine blades, most of them are made by the glass fibers, or some of them using the carbon fibers. So we can add some extra devices around the leading edge of the wind turbine blades. However, people don't want to do that because wind turbine for the aircraft, people will clean the wing of it after each flight. However, the wind turbine blade, it will continue operating for 20 years or 30 years. So people want to avoid those extra devices attached on the wind turbine blade surfaces to make it too complicated and hard to maintain. Yeah.
Thank you.
Okay, any other questions from the students or anyone, whether on the chat or verbally? No, well, if not, at this point, then we are just going to thank Dr. Gao again for very interesting seminar. And I just wanted to let the students know that you have to submit a one-pager for either this seminar or any of the seminars that has been going on throughout the semester. And on Canvas, I see that mostly none of you have done that. So I encourage you guys to please do that. And and then I also wanted to quickly announce the next seminar. So the next seminar is, I believe, 2 weeks from today on April 18th. And that seminar is going to be by Dr. Juan Vivanco from Chile. Okay. So again, thank you, Dr. Gao. Very interesting. I enjoyed your seminar, and I'm sure that the students did as well. And yeah, so the students, I will see you guys in 2 weeks. Thank you so much.
Thank you.
Yeah, bye.